a lot of things go into making the launch access easier, not just the actual mechanical and kind of electrical standardization of the interfaces. And of course, advances in commercial electronics, we can do a lot more with a lot smaller packages. And we also saw an opportunity in the Earth imaging market. The trend in the commercial Earth imaging space is for bigger, more expensive, more capable, so high resolution. And what that means is you're launching these 1, 2-ton satellites, incredibly expensive, so that you have a very limited customer base who can actually afford to use your imagery. And you're also doing point-and-shoot operations. So you have a customer who's typically a wealthy customer who can say, go look into space. So you task the satellite, it looks at that specific area, which means that it's missing everything else around it. So for some satellite systems, they can provide daily coverage of a specific place, but that means that they're not taking imagery of everywhere else. And one of the big motivations for Planet Labs is we want to use space to help life on Earth. And that doesn't just mean that the customers with lots of money life on Earth. That means all life on Earth. And so to be able to design a system that monitors the entire globe and is able to update that every day and then democratize the access to that is the type of impact that we're trying to do with our constellation of satellites. So where technology meets opportunity, we're launching and operating a large fleet of these nanosatellites. And the goal is to image the entire Earth every day and democratize access to that imagery. So if you look at Google Maps, which is typically where a lot of us can get access to satellite imagery, the average age of an image is about 1 to 3 years old. And there's so many things that you can miss if you're only getting an update 1 to 3 years. And what we think is it's going to be a really big game changer to be able to see the entire Earth every day and then start thinking about what you can do with information that's global and also reaching you fast enough to actually do something about it. Like every good Silicon Valley startup, we started in the garage. And this was actually in Cupertino, so the same place where Apple computers were started. And we built the first version of our satellite in the garage. There's about 8 of us. A lot of us came from NASA Ames. We're working on small satellite projects there. A few of the projects that Roger talked about yesterday were spun out of the work that we did at NASA Ames. And we took this idea of being able to use low-cost but very highly capable commercial electronics to use those for more or less disposable satellites that are actually relatively high-performing and at a price point that's reasonable for a commercial company to be able to make profit and survive. We called our satellite the Dove satellite, and it's just another way that we show that this mission is really a peace-bringing mission. And just as a general comment into the small satellite industry as a whole, I think it's pretty noteworthy how many positive applications are coming out of this space, that there's a general sense of collaboration, of positive impact on the planet. And I think that's really wonderful. I see that a lot of the other companies in this space share our same message, and I think that's a really positive sign that it's not a sense of competition. We're all working together to make life better on this planet. The other thing that's kind of interesting about our satellites is we put art on our satellites. So we have an artist in residence program. He was laser etching some of his designs on the sides of our satellites. So you see the shark on the side of this one. And every launch, we do a different design on there. So it's not just that space has a lot of positive applications. It's also that space can be fun or creative or a place where things don't have to be so serious. And you know, I don't know if we'll start seeing this type of thing in the bigger satellites, but I hope so, because it's not that space has to be so hard and serious. We can have a little bit of fun with it too. So it's a 3U CubeSat. It's about 5 kilograms, 90mm aperture. We're doing optical imaging at a resolution of 3 to 5 meters. So it's not the highest resolution satellite, but where the big differentiator is for our product is that it's the cadence with which we refresh our imagery. So the other characteristics are fold-out solar arrays were actually really important for orbital debris. So we increased the surface area by folding out our solar arrays, and that also enables differential drag maneuvering. So for instance, if there was a potential collision with a larger object, if we had enough notice, let's say 24 hours in advance, we can change the attitude state of our satellites to use differential drag to move out of the way. And so when people talk about CubeSats not having propulsion, there are other ways that you can do collision avoidance maneuvering through more or less passive techniques that are important to keep in mind, that propulsion doesn't necessarily mean that's the only way to do collision avoidance. It also has magnet torquers and reaction wheels for attitude control, a star camera, GPS. Pretty much every system that you can imagine in a larger satellite is in there except for propulsion. And we have a predicted 3-year operational lifetime. Again, it's this very similar thing like Jenny was talking about at Spire, that we want the lifetimes relatively short so that we can continuously upgrade the satellites, put in the newest technologies so that we're always flying the latest and greatest. Whoop, what just happened? This is a breakdown of the frequencies that we use. So one of my first jobs when we were starting the garage is to figure out what is our licensing policy and strategy, and how do we make sure we're following all the rules. So advice for satellite developers is start with the table of allocations and read the footnotes. Those are, if you come up with two things, it's those two things. So we use the X-band in the 8025 to 8400 under the EESS. Same for the S-band uplink, EESS. And then our UHF is in the space operations band. So very quickly we realized we were not appropriate for the amateur spectrum, and we moved off of that and selected some more appropriate frequencies in space operation. The approach that we call to this design of satellites is agile aerospace, kind of like agile software. We treat our satellites as if they were software, and we take a capabilities-driven approach. So what is the best satellite that we can build today? And then you build it, test it, fly it, learn all the lessons, and then incorporate that into the next satellite launch, rather than starting from the perfect satellite right away and taking a long time to get to that place. So we're launching early, and often we prefer testing, especially in space, over simulation. And over the last 3 years, we've had 12 full redesigns of our satellite, incorporating new technologies, incorporating new subsystems, improving existing subsystems, things like that, improving manufacturability, because of the scale of which we're talking about launching these things, we have to be mass manufacturing, which is something that is not very commonly done in the space industry. When we launch a constellation of these Dove satellites, we call that a flock. And for imaging the entire Earth every day, we need 150 operational satellites in a single sun-synchronous orbit, which acts as kind of like a line scanner or a string of pearls. Each satellite has a very simple mission: just take a picture once a second, and then when we're in a view of a ground station, we'll dump the data down. This is our launch history. So to date, we've sent 99 satellites for launch, and we've had a number of challenges along that line, but we've had a lot of successes as well. So our first satellite was actually Dove 2, which beat Dove 1 by 2 days. They were going on separate rockets. One of the biggest challenges for secondary missions is that the launches often slip. And so even though you have some idea when you sign the launch contract, you actually have no idea when the launch will actually go, and that makes the whole thing very challenging, especially naming, because then you never know which one's actually going to go first. So Dove 4 was a failure. That was inside of UNISAT-5, which never deployed our satellite. That was okay because we had Dove 3 on there on an ISIS system, which worked, so thank you for that. And then also Flock 1D was on the failed Antares mission, but we were able to turn around and get 2 more satellites on the next Falcon 9 mission to the space station, and that was in 9 days. So from failure, we got a phone call from NanoRacks that said, hey, we have an opportunity to launch some replacement satellites on a SpaceX rocket. And we said, great. And then they said, okay, have your satellites ready in 9 days. So for us to be able to build and test and verify and qualify and be able to ship that in 9 days is pretty fast for the space industry. We have a network of ground stations. We use a 5-meter parabolic antenna for the X and S band. As you see a picture there, we also put art on our ground stations. We put art everywhere. The locations for those are in the US, UK, New Zealand, Germany, and Australia. And the idea is to concentrate multiple antennas per site so that it's a bit easier to do geographic coordination with other X-band and S-band users rather than having larger sites, larger numbers of sites around the world. We try to concentrate numbers of antennas, so up to 5 antennas at a specific site will decrease the footprint where our satellites are downlinking. We also use UHF Yagis for the UHF uplink and downlink. And there's some locations which only have UHF Yagis. And so that's both for TT&C, and we've also been able to do ranging with these things. And so another one of the really important things that we do as good citizens in orbit is that once we've refined our ephemeris through UHF ranging and we have better predictions of our satellite locations than the publicly available TLEs, we then publish that on our website. And so there's a link where you can go to get the most up-to-date and most accurate positioning of our satellite so that you can have better predictions for potential collisions. Yep. In terms of orbital debris, this is the profile of the different satellite launches that we've had. So Dove 3 and 4 were kind of on the upper limit, but still within the 25-year rule. And our ideal orbit is at 475 kilometers, so very much below the densest parts of the debris field. And also, I think this is important to keep in mind, in the kind of pink color is CubeSats generally, excluding Planet Labs, and then our specific satellites. So then the number of space objects that could be considered potential debris, the percentage that CubeSats contribute to is as of today are relatively small. So we have about 100 employees headquartered in San Francisco as well. San Francisco is booming in this small sat industry. 100 plus satellites manifest over the next 18 months, and $160 million raised. About 20 satellites currently operating in orbit, and I think that's really important also to note. You know, we've sent out 99, and only about 20 are operating right now. Many of them have already deorbited because we're going to these low orbits. So when you see these launch predictions for how many satellites are going to be launched over the next couple of years, it's also really important to note how long are they going to stay in orbit. So from a space station orbit, we're lasting anywhere between 6 and 9 months. So even though the numbers at launch sound scary, the numbers of satellites that actually are in orbit at any given time is actually pretty manageable. And we're downloading thousands of images per day. I'll just scroll quickly through some of the examples. These are images that we've gotten from our satellites, these 5-kilogram things. It's a little bit amazing to think the quality of imagery you can get from such a small system. But for agriculture, mapping, urbanization, resource extraction, weather response, alternative energy proposals for solar, maritime monitoring, it's all good.
Excellent. Thanks, Mike, a lot. And we wish you a lot of success with the Planet Lab. And also, yes, Otto, question? Very short.
Short question. How much time do you allocate per satellite for AIV?
For
assembly, integration, and validation.
It depends on how many satellites we have to send out, but on the order of like a couple of weeks. Yeah, so it's pretty short. We can accelerate it if we have a need, but if we want the engineers to sleep and things like that.
Are you doing any burn-in test?
What do you mean burn-in?
Burn-in test. I mean running systems for a certain period of time to get better confidence in the survival of the electronics.
Sure. So what we do is, let's say we have to ship out 28 satellites. We'll build up 35, and so we'll have a bunch of on-ground spares, and then we'll be running tests throughout the whole time that the on-ground spares stay there, so we can compare to on-orbit performance. And so we do have some long-duration tests on the ground as well.
Thank you.
Only this mic is working. I would like, thank you again. I would like to introduce the next speaker, which is Professor Fernando AGUADO, if I say correctly this.
Perfect.
From presenting HUMSAT. Very short from my side. I leave to him, but within 15 minutes limit, to use also your introduction, because on the